The box is sitting on that level surface, and currently its velocity is 0. We know that there is an impinging force of 45 newtons acting at a declining angle of 35 degrees. Box has a mass of 5 kilograms. So what is the size of the frictional force, and what is the size of the normal force acting on the box? So I think this is like a 3-minute question. So that's as long as you get before I pick on one of you. 3 minutes. So Shreyas, can you explain how to do this?
Like starting with the free body diagram.
Great. Can you tell me what you did?
Drew the normal force going upwards, perpendicular to the surface it's on. The friction going towards the left.
Okay, so I'm going to catch up to you. So normal force upwards because it's of the surface it's on. Friction going to the left. Keep going.
The weight going downwards equal to the normal force.
I'm not going to draw it quite equal, but okay.
And then the force, I didn't draw the components on my free body diagram, but I drew the force 35 degrees south.
Okay, so something like that, 45 with your 35-degree angle here. Excellent. Did you decide on a coordinate system that you thought would support this problem?
Yeah, I just ended up with the normal force, weight, friction.
All right, so something like that. And then perhaps like so. So positive x here, positive y. All right, keep going.
And then, since we're trying to find for the friction, and since velocity is 0, the sum of the forces is equal to 0, so 45 cosine 35, the horizontal component, minus friction is equal to 0, so friction is just equal to 45 cosine 35.
Okay, so that's a lot in a single step. So to explain to the folks who've never done it before, it sounds like you took and created two components, here and here, to take over for the force that is there, and indicated that this one is going to be 45 cosine 35, and then the vertical one 45 sine 35. That is taking over for the actual force that was there. So these are the two components that are acting on the object. Now, breaking up into components, you should never do that on your actual free body diagram. We're doing it here because, well, we're trying to solve the problem. We're no longer trying to score points for our judges to give us value points. So I've now got it written so that I have two one-dimensional problems, and just stating over what Shreyas already said, it's 45 cosine 35 minus friction equals 0. So that makes friction 45 cosine 35, which I don't know what that is. Doesn't really matter. I'd say, like, somewhere around 24. What is it? 36. Okay, great. 36 newtons. Questions about that? So next we're going to do the...
Can it be negative? Or do we not have to put the negative?
Your question is not without merit, so let me talk a little bit about that, especially for the new folks. We had to know that it was negative. Well, no, let me say that different. We didn't have to know it was negative at the start of this question. We did know it was negative because of the way we drew our problem, and we put the negative here because we knew it had to be in opposition to the motion or the applied force of the object. Had we not known whether it was positive or negative, we would have had to have put that as positive and solved for it and gotten a negative answer. The best thing to do at the end of this problem is for you to indicate the direction, not necessarily by positive or negative, but by saying to the left. That clearly demonstrates you understand the direction that it acts, but also doesn't make it so that you're just relying on algebra to tell you positive or negative. So it's not a great, clear answer, but it's best I can do. So, Shreyas, y direction. Did you already state that and I just plowed all over the top of you?
Wait, what?
Did you talk about the y direction?
No, not yet.
Go ahead. I'm all ready.
So this time I did normal force minus 45 sine 35, which is the vertical component, force minus 50 is the weight, equal to 0, because once again it's moving vertically.
Great.
And then the normal force is equal to 45 sine 35 plus 50.
Was that 70 something?
75.
75? So upward would be great. So as the problem goes, not particularly interesting, but as a practice exercise goes, it should help all you who are brand new to this, kind of figuring out what to do. This is a series of steps. Even if you have no idea where to start, it should give you a good place to start and a solid foundation for you to get to a point where you can start figuring out the size of the forces. Remember, a Newton's law problem can only ask you to find the size of a force or an acceleration. Which brings me to my follow-up question here. Let's assume that something happens where you're able to break the static friction and the box began to slide. And the moment that happened, the frictional force was cut in half. Were that to happen, what would be the acceleration of the box under that circumstance? I'll say it again. Something nudges the box and you break static friction. The box begins to slide, but the friction has been cut in half. What would be the acceleration of the box under that circumstance? I'll give you just a second. It doesn't take much time to figure this one out. Probably enough time, especially for the people who have done this before. So let's see. Who should I pick on at home? Hey, Sam, can you walk us through this?
Okay, I haven't finished it on my calculator, but I've written it out.
All right.
So we told us that F would be over 2.
Okay.
So what I did was I did E of Fx, which would equal ma, because it's moving,
Okay.
equals 45 cosine of 35 minus F over 2.
All right, the biggest switch is that now we have a net force equal to ma because the forces are unbalanced. And we have two forces acting. We still have the 45 cosine 35. That hasn't changed. But now the frictional force that we found earlier has been cut in half. And how big is that?
Like 18.
Because it was cut in half. That has to equal ma. So the truth is, since it's been cut in half, this whole left side is 18. So I assume you get something like 3.5 or 4, probably 3.5. 3.6.
Yeah.
The system begins to accelerate is the important repercussions there. Questions about that? Go ahead.
So can a problem just start off as the e to the f of x equals ma? Like from the start, the forces are in balance?
Yeah, you can know, anytime the object's accelerating, you know the forces are unbalanced, so you'd start with net force equals ma. All right, so this one, not changing it too much, but definitely want to see, provide you with the range. So this is one that anybody in a physics class would have already seen. And although it's not particularly interesting, it, kind of uses a different set of skills. So most of you guys remember one like this where I have maybe a kind of a box that's going to be hung so that there's two cables supporting it. Maybe a cable here that's perfectly horizontal and a cable here. Perhaps at, let's say, 40 degrees. Tension in this cable, tension in this cable to hold our box, and our box, let's say, is 50 kilograms. So in this environment, what would be the tension in each of the cables suspending the box? You guys from last year remember these? Yeah, not terrible. Not interesting either. So, take a few minutes and find somebody to help us out with this one. remember, your first free body diagram shouldn't be components. Ernesto, can you tell me what I'm supposed to do here?
The free body diagram, you put weight going down,
Perfect.
then T1 going right, and then T2 going diagonally left.
Excellent, thank you.
And then I divided it up into components and then did mg going down, T2 cosine theta going left, T2 sine theta going up, and T1 still going left, right. And then I did,
I'm going to pause you for just a minute. Just give me
okay,
a second to get caught up. So for those of you who are new here, still trying to figure this stuff out, the original free body diagram should have looked like this. All by itself, these represent the three forces acting in the system. They are the only forces that actually act in the system. Ernesto is going a step further now to actually solve the problem. And it sounds like you decided to do a coordinate system that was lined up with the weight. Is that true, Ernesto?
yeah.
All right, so let me draw in a coordinate system so that I have the basis for what you did for X and Y. So positive Y. Did you do positive X to the right?
Yes.
So the next thing it sounds like you did was you, using this 40 degrees, wrapped a triangle this way with one component here, T2 cosine 40, and
Yeah.
one component here, T2 sine 40.
Mm-hmm.
Okay. Now, once we've done that, all of you guys who are just new to this, that is taking the place of T2. So T2 is unnecessary here once we have its components registered. So I'm just going to take a moment and move the other Y component here so that they're all along the axes. This is not necessary to do the problem. It's just to ensure that you guys who are kind of coming to this new recognize that we are trying to create one-dimensional problems. So, all right, go ahead and finish up. What do we have to do after that?
And then I set up T2 sine 40 equals to mg, which is 500. So T2 equals 777 newtons. And then I said T1 equals to T2 cosine 40, which gave me 596 newtons.
Perfect. That's it. Pretty straightforward. Couple things to point out here. AP1, you know, this problem would have been a little bit more difficult because in AP1, generally the students that are there are still struggling with their trig, still struggling with sine and cosine, all that kind of stuff. But they can be asked questions like, you know, do you expect T2 to be greater than or less than the weight of the box? And without doing any of the work, it should be clear that T2 has to be greater than the weight of the box because T2 has to not only lift the box and keep it from falling, T1 doesn't do that at all because T1 doesn't point upwards at all, but T2 also has to balance the fact that T1 is pulling the box sideways. So there's optimization opportunities here. Chances to find out what angle would reduce the stress on T2. In addition to that, the problem can be turned around, where perhaps there's a maximum tension that can be withstood by the cables, and you have to figure out what is the mass of the sign that can still be held under the constraint of the maximum value the cables can hold. So if I say that the cables can only hold a maximum of 600 newtons or they snap, what's the largest box I can put there before they snap? So Mr. Calvo is pointing out something about why nobody's questioned the facts that we're putting a 110-pound box up in the air and we're just, holding up there by strings. I don't know. There's some very decorative signs out in front of, people's storefronts. Perhaps this is how they want to hold it there. If it's lit and it's got lots of, light and glass and stuff on the sign, it could be heavy. I don't know. Kind of like the idea that you're living dangerously and anybody could walk under it. But Alex wanted to make sure that we, had an opportunity to discuss that because he's throwing out there in the chat that information. So, and then there's all sorts of extra, people putting stuff in there. So you guys should all log in sometime to be part of the chat. It's not as much fun as it sounds, though. All right, so again, we have a straightforward inclined plane, the simple machine. It's got an angle of 40 degrees. I place a 5-kilogram box on it, and it's frictionless. Doing the full process of a free body diagram and everything, tell me what the acceleration of the box is down the ramp. And I'll pick on somebody here in just a minute. Okay, so you put the Y direction lined up with the weight? Okay, I probably wouldn't have done it that way. And not to be not to burst your bubble on it, but there's 3 priorities when we try to take a look at the how we draw in our coordinate system. And although you can work this problem, oops, bless you. You can work this problem by doing it that way, by putting my coordinate system lined up with the weight. I actually make the work that has to be done now more difficult. And here's the reason why. If I think the box is going to move, and it's a frictionless surface, so I was asked for the acceleration, I think it's every reason to believe it's going to move. I'm pretty confident that the box is going to accelerate this way down the ramp. If it does, and I've chosen my coordinate system to be shaped like this, I'm putting myself in a position where the acceleration itself is going to have a component in the X direction and a component in the Y direction. Now, that's more work, and I think it's going to be a challenging bit of a problem. So instead, to make the problem a little bit easier, I've always recommended that you use a certain set of priorities in designing your coordinate system, with the number one priority being to put the coordinate system in the direction of motion or in the direction of the acceleration, which would suggest a coordinate system that's lined up like this. Because if I do this, that puts my X direction in the likely direction of the acceleration of the system, which means that when I solve this problem, I think I can then state that the net force in the Y direction is 0, and the net force in the X direction is equal to ma. Now, that being said, I do have to deal with the fact that the weight is not in the X direction or the Y direction. And for you novices out there, you need to come to grips with this is 40 degrees. The angle between the weight and the Y-axis is always the angle of the incline. Always. Yes, Valerie?
Why is it 0 for the y-axis?
Well, I don't think there's any chance that the box itself is going to accelerate that way. Do you? No. And for a similar argument, I don't think there's any chance it's going to accelerate this way. So when it comes to accelerations, I don't think it's going to do either of those. I think the only likely direction of motion is up or down the ramp, since the ramp prevents it from doing anything else. Good to go? All right, so we're going to go ahead and take that weight and break it up into 2 components. So I'll have mg cosine theta in the y direction and mg sine theta in the x direction. And here's where anybody who was in physics last year, hopefully we come to remember that when we have components for an incline, the weight will always break up in this way. If you wish to commit it to memory to make things go faster, I'd highly encourage that. Yes, it is possible that we won't have the system lined up in this way. There are situations where it is better not to do it this way, and we'll see them. But for the basic problem where you know the object's going to be moving up or down the ramp or stay still on the ramp, this is probably the best way to go, and it's the fastest way to go. And it allows you to commit these to memory, which for multiple choice, that benefits us a lot. That being said, That means normal minus mg cosine theta is equal to 0. And it also means that mg sine theta is equal to ma. And the reason I did this the way I've done it like this is so that when we cancel out the m's, you recognize that for any incline, the acceleration down the ramp is going to be a percentage of g. And doesn't matter, it doesn't base on the mass. So I'm not going to spend time. You guys put the 10 sine 40 degrees in there and get the actual answer. But I want to point out that this is worth considering for a lot of these problems. It's in your best interest to have this ready to go for incline problems. Which brings me to the last thing I want you to consider. Look, those are the basic kinds of questions, but we're not going to be doing that. Tomorrow, we're going to start working on problems where we have static and kinetic friction. We're going to be trying to focus a little bit on inequalities, and we're going to ramp up the level of difficulty to be more in line with what we have in this class. For you guys who are novices, take a look in chapter 4. This is where this stuff is. Take a look at some of the basic problems, work through some of the examples. If it were me, I would just take a look at the example sections, cover them up with a Post-it, work the question, pull off the Post-it, and see how you do. It'd be appropriate amount of time, appropriate amount of practice. But we're going to start moving towards other things, like we want to talk about drag. Although we haven't talked about it in here yet, and we haven't talked about it much in first year physics, the force of drag is a force that is proportional to the velocity. It also can be a force that is proportional to the square of the velocity, depending on the type of drag that we have. This coefficient out front isn't the same in these two, because there are different kinds of drag. There's laminar drag, which is more smooth air, and there's turbulent drag where the air is stirred more. Turbulent is more difficult, it's more random. Laminar is more predictive. But in both cases, there's a relationship between the force and the velocity. So I want you to imagine if you had some irregularly shaped object and you were to drop it. Gravity would pull the object down, but drag would try and prevent the object from going downwards. There'd be a drag force upwards. Now, the next two questions I'm going to ask, we might not be able to answer before the bell rings, but I think the quick-witted in here probably will get to it nice and quick. If I merely drop the object and say that when I drop it, that's time equals 0, what would the acceleration be at time equals 0? And then to follow that up, what would be the acceleration after a period of time has passed? Think about that for just a second. Let it roll around your head. When you first drop the object, how fast is it going? All right, so I hear one person say 0. And I'm hoping that more of you realize that when you first let go of the object, its velocity is 0. So in answering this first question, at t equals 0, the velocity is 0, which immediately means the drag force is also 0. So when you first let go of the object, it doesn't have any drag. The only force acting on it is gravity. It accelerates at g. But that acceleration causes a change in the velocity immediately, which means the moment it begins to fall, it has a velocity, and because of that, begins to develop an upwards drag force. Are the forces balanced immediately? Or are they unbalanced? They'll stay unbalanced for a while, which means that the object's velocity will continue to increase. However, after a long time, the acceleration should make it so that the net force is zero, where the drag force continues to increase in size because it's accelerating until it reaches a point where these two forces are balanced. Because at that point, the acceleration would have to equal zero, and we're in a steady state condition. In fact, at that point, the downward force of gravity would have to equal the upward force of drag. This is a special condition known as terminal velocity. All objects that fall through the air will eventually reach terminal velocity. All right.